Alright, so here we have a question that's reminiscent of the type of questions we've been asking before. But instead of the good old fashioned vectors in Rn, what we're looking at are a bunch of polynomials. In particular, we have these four polynomials over here, and we're asking if they're linearly dependent. And what we want to see is that while the form of these polynomials differs quite distinctly from a vector in Rn, in practice as a vector themselves, they're not much different. So we're going to see that here in just a second. But to start with, we should take our four vectors and, as we've done before, rephrase this as some sort of polynomial equation. Now, if they're linearly dependent, which is the claim, as before, I should be able to take combinations of these three polynomials and achieve this last polynomial somehow, right? That should have some sort of equation. So in other words, it's the claim that y1 times the first of our polynomials, right? We're not going to treat these any differently than we would have treated vectors, but I do want to change the x's we used before to y's because I don't want to get confused with x's here, right? So let's say y1, first polynomial, plus y2, second polynomial, plus y3, third polynomial, all of that should allegedly be able to be combined to be the last of these polynomials. Right? And so if in fact these vectors are linearly dependent, then that should be the case. Or so this has a solution. Now, having said that, we did all of this work in Rn. We would like to reconnect this to Rn in some way. And the way we see that is, look, if I expand out everything on the left-hand side, right? What happens to my x cubes? We'll have a minus 4y1x cubed, a minus 5y2x cubed, a minus 5y3x cubed. And all of that should be equal to 10x cubed, right? The x cubes on my left should coincide to the x cubes on my right if in fact this is an equality. So essentially what we're saying is minus 4y1 minus 5y2 minus 5y3 should be 10, right? And then shouldn't the x squareds play out the same way? Shouldn't 2y1x squared plus 3y2x squared plus 3y3x squared be equal to minus 6x squared on the right? And then our first powers, minus 1x's, y1x's, 5y2x's, 1y3x's should be minus 10x's, and finally minus 6y1's, 2y2's, minus 4y3's, all of that should be minus 4, right? And so we've come to a situation where we have a solution to the polynomial equation we wrote if and only if this system of equations represented by this augmented matrix has a solution. So why don't we check it out? Alright, so let's go ahead and start popping in our rows. Minus 4, minus 5, minus 5, 10. Two, 3, 3, minus 6, minus 1, 5, 1, minus 10, minus 6, 2, 4, negative 4, sorry, negative 4. Alright, so let's go ahead and evaluate that. And we end up with this reduced row echelon form matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, minus 2, 0, 0. And so what we should observe from seeing this is, hey, look at this thing. Let me go back to the screen here. What we should observe is, looking at this is, as a system of equations, what this is telling me is that this has a solution. y1 equals 0, y2 equals negative 2, y3 equals 0. Right, if I put my augmentation there. And that actually is totally consistent. If I take my second polynomial and I take minus 2 times that, I readily, in fact, get the fourth polynomial. So, having done that, let's go ahead and note that this, in fact, does have a solution, since the polynomial equation above has a valid solution. This set of vectors, or this set of polynomials, are dependent. Alright, thank you very much. See you in the next video.